Hey everybody, welcome to the Taku Glacier in Juneau, Alaska. I'm Caitlin Sachs, a senior producer for Nova, and I am in this amazing place with a team of incredible scientists, including Zoe Schlossnagle from Washington University in St. Louis, and Jaiden Zach from University of Wisconsin-Madison, two grad students who are here studying this glacier. They and their team have been carpeting this glacier, doing all sorts of different kinds of measurements and studies to better understand this glacier. We're going to get into all of that in a little bit, but I just want to welcome people to join as we do and give you a little bit of a preview of what we have in store for you. We're going to talk a little bit about why this glacier is so interesting. We are going to talk about the different kinds of measurements they're doing, stuff like measuring icequakes, drilling holes to the bottom of the glacier to understand what's going underneath it. We're actually going to do a little demo. They're going to show us how they measure and try to catch icequakes. We're going to do a little tour around here and explore some ice cracks. I promise we will not fall in them, but we are going to show you some because they're all over the place right here. And finally, we're going to show you this drill behind us, which is actually drilling down to the glacier bed. And we're going to look down that hole, see what that's looking like. They're not quite to the bed yet. And hear a little bit more about that drill. So if you're just joining us, welcome. We're here on the Taku Glacier live. We are going to be getting audience questions. So if you have questions, put them in the chat. The Nova team is going to send them to me. I'll get them on my computer right here. So put your questions in the chat and I'll make sure to get them to Zoe and Jaiden. All right. So, hi. Welcome.
Hi.
We're live. So you both tell me a little bit about who you are, how long you've been working on glaciers.
I just finished my first year of my PhD at WashU, and this is my second field season out here on Taku Glacier. I've been looking at the data from last season for the past year. Excited to get more.
Jaiden.
I just finished my third year in my PhD at University of Wisconsin. Like Zoe, this is my second year on Taku Glacier. I also did a season in Antarctica on Points Glacier.
Very cool. So let's talk about Taku. Why this is a very unique. You're here for a reason. Why is this glacier so interesting?
Well, first of all, it's enormous. It's the largest glacier, I believe, in at least the Juneau ice field.
Do you have a sense of how big?
The surface area of it is about 750 square kilometers from the ice field down to the terminus. It's huge. It's about 5 miles across. But what makes it really special is that it kind of has this really unique velocity behavior. So the eastern side of the glacier hits its peak speed several months before the west side of the glacier.
So let's talk about that a bit. When you say velocity behavior, yes, this glacier is actually moving.
Right.
It's slow. So explain that.
So glaciers flow in a combination of two mechanisms. One is it's deforming under its own weight and flowing itself. And then also it's sliding across the bed. So at the dirt ice interface, essentially it's sliding. So what that means is that the east side of the glacier is hitting its maximum speed in a combination of those two ways in about March, and the west side hits its max speed in around August. And so it's kind of like shimmying forward a little bit in time.
And this glacier, and you're interested in studying how glaciers are flowing because that's ultimately sea level. That's right. You know, a lot of people think it's the poles are melted, but it's not exactly melting. It's really these glaciers moving that is the big contributor to sea level. Yeah,
Especially in Atlanta.
Yeah, it's a combination of those things. So there's a lot of melt that's going on, especially on glaciers like this, where it's right now it's well above freezing, so there's a lot of ice melting. But also it's flowing downhill into warmer areas where it can melt out.
and so Taku Glacier is this great natural laboratory. It's got this very special feature. Right. Explain about that. What is so special about the way Taku is working?
Well, we don't really know a lot about what happens at the bed of glaciers, which is a super large control on how fast they flow. So having two sides that exhibit two different behaviors means that there's likely two different bed situations, I guess. There's probably different water flow patterns. There's different maybe rock types. There's different levels of friction. And so we kind of get like two glaciers in one, essentially.
So we have two different sides of the glaciers flowing in different ways.
Right. And they're both subject to the same like atmospheric controls, the same everything. It's pretty
Same
awesome.
glacier, same river they flow into, but one moves in a different way than the other.
Yes.
So you can really kind of control for a lot of variables. But then look at how different, like, start to try to figure out what makes it glaciers flow. So let's talk about icequakes. I know we're in just a moment, and if you're just joining us, welcome. We are on the Taku Glacier. And in just a moment, we're going to show you how they detect icequakes. We're also going to go take a look at one of the large crevasses over there. And we're going to show you what's happening with this drill rig. If you have questions, put the questions in the chat, and we will get them. I have a computer right there, so I'll be able to ask Zoe and Jaiden these questions. So let's talk a little bit about icequakes. What are icequakes?
So icequakes are they're like earthquakes, but they're smaller and they come from a variety of sources in the ice. They can be from cracks at the surface opening. They can be from sudden slip events at the bed of the glacier. Be from a lot of things.
And so you use seismometers to try to detect these things. And you're gonna show us how you actually install these seismometers. Yeah. So I'm gonna go grab the camera so I can show this.
Okay.
And Jade, why don't you guys give us a little demonstration?
All right.
All right.
Drill a hole.
Okay.
So the first thing we do in order to install a seismometer is we drill a hole. This is something that we have to do on glaciers that are melting and the ones that don't have snow on the surface. So in a place like Antarctica where we might have snow on the surface, this wouldn't be a necessary step. But here, since the surface is melting, we want to drill it down because as the ice melts over the next few days, we don't want our seismometer to just fall out. So I'm going to start by drilling a hole.
Is it hard work?
It's hard work. Trying not to huff and puff too much, but it's definitely hard work.
While you're working on that, one of our audience members asked if it's safe to drink the water off this glacier.
It is. That's actually our primary source of drinking water and water for cooking.
And it tastes delicious.
Tastes great. Very refreshing. Bring the ice tips out of the hole just to make it a little easier to drill. Is that heating?
But you're not
This is the seismometer. This is what we're going to be putting down the hole. I'm going to catch my breath.
You can hand it off to Zoe if you want.
Yeah. So what I'm doing right now is heating up essentially a mold of the bottom. So we're gonna melt the shape of the bottom of the seismometer into the ice to get really good contact between the spikes on the bottom of the instrument and the ice.
Okay, so let's take a look at that mold again.
Yeah.
I see. So those are the exact same shape. So you're heating that up. And is that just a regular camping stove?
Yep.
All right.
With some homemade additions. Yeah, essentially we need the spikes on the seismometer to be really, really well coupled to the ice to get as accurate of data as possible. If it wiggles around, if it tilts over, or if it spins, it's gonna not do as well, essentially.
And then how many of these do you install?
So in the past 2 days, we've put 29 out on the east or the west side of the glacier. And on this side, we're going to put in between 50 and 58 TBD, minimum 50, in like a dense grid.
And why do you need so many?
Having a lot makes locating these ice quakes way easier, especially within the array. When you have, it's called like azimuthal coverage. So if you have multiple seismometers record the same event at different times, you can very easily pinpoint the location.
Can you explain that a bit? How do you pinpoint the location? Is it
So you take the difference in time that it took for each seismometer to see the event, and you can kind of trace it back to where it came from. Like think of it like triangulation a little bit.
how long does this take to heat up?
And it's
Yeah, it's about 5 minutes. It's this tool that we have that's the same mold as the seismometer is made out of copper because copper is really good at conducting heat. That makes it get hot faster, but it also allows it to melt the ice faster once we get it in contact in the hole.
Cool. So tell me a little bit more about why ice quakes are interesting.
ice quakes at the base are interesting because they can tell us a lot about how glacier is sliding rather than flowing, and how glaciers are sliding is not really well understood. And so locating them can tell us where these like sticky spots are. So where a lot of the times in glacier flow, the glacier is sliding over the bed like this, but it'll get stuck on something. Maybe it's a hill, maybe it's a different kind of rock, maybe it's a weird pocket, nobody knows. And it'll get stuck, but the glacier will want to keep flowing, so it builds up stress and it builds up stress, and then all of a sudden it slips. And that's called stick slip. And that's it's really interesting to look at. We don't really understand what controls stick slip. We don't know how it relates with like things like water pressure. Is it actually a topographic high? Is it different kind of rock? And those slip events can facilitate really fast glacier motion, which is important for things like sea level rise.
And to add to Zoe's explanation, when we measure these stick slip events like Zoe described, that's one of the only ways we can directly measure slip happening at the base of the glacier, which is, it's a very difficult place to access. We've got this huge setup over here to drill a hole to look at just one, relatively small area of the bed. When we put these seismometers in, we can listen for these events coming from the bed, like Zoe described, and that gives us an insight into what's actually happening down there.
And so explain a little bit more about how the different sides are moving differently. The different halves of this glacier are moving differently.
So the east side of the glacier is speeding up through the spring, and then it hits its maximum speed in March. And then after that, it kind of slows down and mellows out, but it's still flowing. It's flowing the whole time. And then the west side speeds up through the spring, but keeps speeding up throughout the summer and hits its peak around August before it starts to slow down again. And the hypothesis behind why this is happening is that there's two different water drainage networks beneath each side. So what happens is water from melting and warmer temperatures will be routed to the base and it'll pressurize, which makes the glacier slide faster. Think of it like you're lubricating the bed a little bit, so it's slippery. But what will happen is when there's enough water, the hydrologic drainage system might reorganize into something that's channelized and lower water pressure. So it's efficiently evacuating water out from underneath the glacier, and the glacier can kind of sit back down on the bed and slow down.
So cool.
Yeah. So we think that's happening on the east. We don't know what's quite what's happening on the west.
How are we doing here?
We're getting pretty close. I think we can have a go.
Okay.
We have this. So on our seismometer, we've got a north arrow. These seismometers record motion in 3 directions. They record vertical motion and horizontal motion in each of the 2 directions. So what we want is to get this arrow pointing north so that when we go back and look at the data later, we know which horizontal direction was north-south and which one's east-west. So in order to get that north, we have to align these spikes in the correct direction. So if you take that, the way we do that is stove off. We've got a line on the surface and a spike in the front. We want that to be pointing north. So we've got a compass on the ground there. And then what I'm gonna do is I'm gonna eyeball it. We'll get it close and then we'll measure how well we did after. I'm putting this down into the hole, putting it in contact with the ice. And now I'm gonna lean on it and put a lot of weight in order to melt this copper piece into the ice. This will take a couple minutes.
Okay.
Yeah.
While this takes a couple minutes, just a note for those who have just joined us. We are at the Taku Glacier in Alaska with a team of scientists studying this glacier. And if you have questions for them, you can put your questions in the chat. I'm going to grab my computer right now and ask you a few of these questions we had from our audience. So folks want to know, why does the snow look so dirty?
Why does the snow look?
I got one. Come on.
I don't-
A lot of dirt will blow onto the glacier by wind. It'll come off the sides of the mountains there. And as the ice melts, it just accumulates because the ice is melting, the water's flowing away, the dirt's not going anywhere. So the dirt has had a lot of time to accumulate as it just blows onto the glacier from wind or falls off from the sides of those mountains there. And yeah, so it'll just concentrate on the surface.
Are there any microorganisms in the water?
I don't know.
They're not microbiologists. Okay. What is the coolest thing you found in the ice? And I believe the cool was pun intended there.
Oh. Well, that I found, I haven't found anything, but yesterday one of our teammates found a jawbone with teeth in the ice. So
We think it's from a deer.
yeah, we think it's a deer. But that's pretty cool.
I'm a little bit biased, but I think the very round rocks that we
Ooh,
find at the
yeah.
front of the glacier are pretty cool. The glacier grinds them up underneath and turns them into very spherical rocks, just like a super efficient rock tumbler.
How's this coming?
We're making progress. We've still got a ways to go, though.
It's very physical work, huh?
Yes.
It is, yeah.
You must eat a lot while you're here.
Oh yeah.
Okay, some more questions. This one, ooh, could an icequake lead to a yokel in a glacier if the glacier surroundings are weak? So a glacial outburst flood is a yokel.
Yeah, they could. In general, the ice quakes are actually small in magnitude. So while it is moving in like a burst of motion, they're usually moving less than a millimeter. And so those floods are usually caused by continual melt from other causes. But the ice quakes could be a part of that equation.
Do you have time for one more question, or are we almost there?
I think we've got time.
Yeah.
All right, folks want to know what kind of wildlife you've seen.
This year, I haven't seen anybody yet, but last year we had some moose visitors. We had a mom and two calves and then two teenagers come and hang out at camp. There's a pack of wolves that lives around here. I've heard them and seen their paw prints, but I've never seen them in person. And yesterday, 2 days ago, there was a black bear that was seen on the ice. He comes
Just-
up every once in a while.
It's just up there, about a half mile away.
So how do you sleep at night?
Pretty good. I'm pretty tired at the end of the day. Doesn't bother me.
Tell us how we're doing. Almost ready?
Yeah, ready.
Ready.
Yeah.
All right.
So if you want to show, we've got
we
these
can
spikes
see the
melted. You
spike.
can kind of see them through the top there.
Oh,
Cooled up with water, but
not super showing up on camera.
All right.
Okay.
you have to take our word for it.
Yeah. And then I'm just gonna take the thermometer. See how good of a job Jake did.
It did all right.
All right.
Then we'll measure the angle. Go. How do we do? 351. So I was aiming for 360 or 0, true north. We'll just have to correct for that later when we process the data.
Very cool.
We gotta make sure to take that down in our notes too.
Yes.
So from here, this is not actually a seismometer. This is not actually a place you care about seismometer readings right next to a drill. So you're going to pull this one out, but what would you do from here if not?
Well, we would turn it on and then we would tie some paracord to the little loop and tie it to like a piece of bamboo that has a flag on it so we can find it later. And then we would bury it in the ice. Like that. And then 4 days later, we'd come back up and drill a new hole and put it back.
Cool.
Because in those 4 days,
Yeah.
the ice is going to melt down and the seismometer is actually going to probably be falling over on the ice. So we'll need to set it back up again.
Yeah.
And then does it send you data by like satellite, or do you have to just collect it again to get the data?
You have to collect them, and we have readers back in St. Louis and in Madison.
We won't be able to look at the data for another month or so.
Yeah.
Cool. All right, well, let's come sit back down here because I want to talk about what this drill is behind me.
Okay.
I'll need to set the camera back up. Viewers at home, your production team is just me right now, so apologies if it's a little rough. That looks pretty good. Okay. Oh, I need access to Google Document. That's Nova at home. Oh, there we go. Got it.
Okay.
Okay. Have you ever found meteorites in the ice? And what are people in the back doing? We'll start with you. No.
Not in this
No.
glacier.
Okay, let's talk about this drill. All right. You're measuring icequakes to understand movement. The drill is going to the bottom of the bed. What's that?
So when we do seismology, we're taking basically indirect measurements of the base of the glacier. We can cover a wide area. We can learn a lot from these indirect measurements, but if we really want to know exactly what's happening, we actually have to physically access the bottom of the glacier. So what they're doing right now, they're using a hot water drill, which hopefully you'll get to see up close a little more later. They're using a hot water drill to melt a borehole down to the bottom of the glacier, and then we'll be able to directly access the material beneath the glacier in order to study it.
And so what kinds of instruments are you going to be sending down?
So one thing that we'll do is we'll use what's called a gravity core. This is used to take a sample of the material beneath the glacier. It's basically a cylinder that we use gravity to drop it into the material that we believe will be like a soft sediment material, and we'll be able to bring some of that material back up to the surface. So that's one thing. Another thing will be what's called a plow meter. This is a device that was custom built for this experiment, and it's very technical. It goes down and it hammers itself down into that sediment. It's got a heavy weight that hammers itself down in, and then as the glacier continues to flow, it will drag that sensor through the sediment and measure how much force it takes to drag it through that sediment.
Any others?
Yeah, so we're in order to study the water system and how easy it is for the water to flow to the glacier, we're going to do some tests where we measure the water pressure. We'll drop a big cylinder attached to a cord. We'll drop a cylinder down the borehole to displace the water, to raise the water level, which will increase the pressure. And then we're going to measure how long it takes the pressure to go back down. Once the pressure goes back down, that will tell us that all of that water that we've displaced has evacuated out through the bottom of the glacier. And then we'll pull our cylinder back up.
You're really just taking every measurement you can think of on here.
Yeah, these boreholes are not easy to drill, so you want to take advantage of having it.
And there's one other that we saw. Tell us about the radar. What's the radar situation? What's that doing? How's that work?
Have some teammates that are doing radar surveys, and primarily this is to get good images or like of the geometry of the bed. So we actually don't know how thick the glacier is. We're standing on it and we are drilling through it, but we don't know how far the drill is going to go down. But these radar surveys are a good way to get, they send pulses that reflect off the bed and come back, and that tells you how like deep the glacier is. So they have been walking around with the radar in the east and in the middle, try and get like bed topography and geometry.
So if you're just joining us, we're live from the Taku Glacier in Juneau. In just a moment, we're going to go check out some of the an ice crack that's around here. We're also going to go check out that drill. But if you're just joining us, know that I am getting questions sent to us on my computer right here. So you can put your questions in the chat. I'm with Zoe and Jaiden, who are scientists working on this glacier. But before we go check out that very cool ice crack in just a moment, tell us a little bit more about what it's like to live on a glacier. So how long are you here for, and where are you? Where is there a hotel nearby?
I wish. I'm here for about a month, and you're here for.
This year I'm here for 2 weeks. We've got some people here for 2 weeks up to a month. Yeah.
And we are all camping at a little kind of island that abuts the glacier, that has an airstrip mowed onto it. And so we have our tent and our bathroom and our kitchen all set up. And so that's where we go make dinner every day.
And how far away is that?
From here, it's like
3 or 4
3
miles.
or 4 miles. Yeah.
How much do you end up walking, or how far do you end up walking around on this glacier?
Yesterday my watch told me 11 miles. Day before that, it was also 11 miles.
And how cold does it get? I mean, it's summer here in Juneau.
Right. I don't know how cold it is right now.
It's probably gets into the 40s at night in camp, but you know, as soon as you walk up near the ice, it's a giant block of ice. It's gonna make things a lot colder.
Yeah.
So you see, I'm starting to shiver here a little bit. I put on another layer.
Okay. Yeah. Well, let's get you moving.
All right.
We're going to go check out an ice crack down here. If you have questions, put them in the chat. We'll come back and get to them when we get back. But we're going to show you a little bit about how what it's like to kind of traverse this landscape. So show me the way. Oh.
We walk around on the glacier. We have micro spikes on our shoes. It looks like one of mine.
Show me those. Oops, sorry.
They're like, yep, little chainmail thingies. And basically just so I don't fall the way I wear them, but here.
Okay. We're going to be very careful here.
No.
So as you're walking along, you run into these things all over the place. And if we're quiet for a moment, you might be able to hear it. I don't know if my phone's audio will pick it up. So these are all over the place. Yeah, I'm going to back up before I stand up. What do you do about that? How do you get across?
Well, not a lot of walking in straight lines.
Yeah.
We want to get over there. We're gonna have to zigzag around all of these cracks to get there. So that's how 3 or 4 miles from camp to the work site turns into 11 or 12 or 15 miles a day.
And how do these things form? Are these interesting to you scientifically at all?
Yeah, they're super interesting to me. So crevasses form because the ice, as I mentioned earlier, is flowing over under its own weight. So it is moving like, it's called like a viscous fluid, super viscous. But sometimes it flows at the surface a little bit faster than it can keep itself together. And so it will split and fracture like a rock, essentially. And so as the glacier's flowing, all of these different stresses are pulling on the surface and they're pulling cracks apart. So that's how these things form. Often they route water through them or I guess.
We try to get it again because I know the audience likes seeing stuff like this. So is this one that you would jump over, or would you go around this one?
I go around this one.
I go around this one. Yeah, I don't.
Especially when we're live.
Yeah. Anything that looks big enough to swallow me, I don't want to jump over.
Exactly.
What would happen if somebody did fall in one?
Well, we've got harnesses and ropes if they're within reach that we can toss down to them. We can do our best to pull them up. Luckily from here, we're also not too far away from Juneau where more help can come at a moment's notice.
And how deep are they?
It depends. Some of them can go all the way to the bed,
Hundreds
which
of
is
meters.
hundreds of meters. Yeah. A lot of them are like 20, 30 meters deep. But yeah,
Pretty serious.
Yeah.
too serious.
You both seem fairly relaxed around them, though.
Yeah, I think it's
Maybe we weren't as relaxed the first time we
Right.
were up here.
yeah. I got used to it, I think.
And something that's unique about this type of glacier where the surface isn't covered with snow is you can see the cracks, which makes
Yes.
it a lot easier to get around. On a glacier that's covered in snow, you have to be a lot more careful because you can see behind us snow sometimes bridges over these crevasses and then it covers it and you can't tell that there's just a chasm below you. So on a glacier that's covered in snow, you need to take a lot more precautions for the risk of falling in. But with this glacier, we can see all the cracks around us. So we just have to be extra careful that we pick a good route to walk.
Just have to watch your step.
Watch
Yeah.
your step.
Okay, well, let's watch our step as we head back to the computer, see if there were any questions that came in from our audience. And then we will go check out this drill rig over here. Oh yeah, we've got some questions. All right. Whoop, sorry. Again, if you're just joining us, I am the only production crew member here, so it's a little rough and tumble. But here we go. Okay. So will cracks expand at all, or are they stable?
They expand, but very slowly. They're, I would say, stable. And when you're walking around,
They're stable on human hiking times.
yes. Yes.
Last year, over the course of the month, we noticed some of the cracks that we were walking past every day get wider and wider. Where at the beginning of the month, we were stepping over them, and by the end, we thought that's a little bit of a long jump, so we had to start going around.
Yeah.
But Zoe's actually got an experiment where she's measuring the speed that a crack opens,
Yeah.
and it requires very precise instruments to actually see the crack open over a week or so.
Well, cool. So you do actually measure how fast it opens.
Yeah, I'm gonna try. Don't know if it'll work yet. We set it up yesterday, so cool. I'll see in a week.
How long did this project take to organize and implement since its inception? Or is it ongoing?
It is ongoing. This is our second field season, so we came out last year. And we only did passive seismic and we did some
passive seismic
Yeah.
is what the demo we did
Yeah.
earlier in the video. If you're joining live now, rewind later.
the passive seismic is when you set up a whole bunch of seismometers and let them record and you don't do anything. We also did active seismic, which involves setting up again a whole bunch of seismometers, but then generating a pulse or a synthetic event. So we used an air gun and a sledgehammer. And
Very high tech.
a lot of people will use explosives or things like that. And basically that allows you to measure for reflections off the bed. And we're not doing that this year. That was all we had last year. So it's a big step up this time.
I've observed how much of the science is like running to Home Depot. We actually just earlier today, right before the live stream started, had a helicopter deliver a single part for that drill rig.
Essential single.
An essential
Yeah.
single part. But a lot of it is you built your own instruments.
Right. Yeah.
Yeah, so again, to mention Zoe's experiments on the crack yesterday, those are made in-house in Wisconsin. The plow meter, that's also custom built. Trying to look around at what else is custom built. We built these copper melt-in tools.
Right.
A lot of the equipment we use is custom built for this work.
And so in terms of like planning for this, I mean, I happen to know that they had a very intense looking spreadsheet just for the logistics, right?
Yeah.
Counting up, number of people days and how many, packets of potatoes each person needed. How long does that take to sort of, how do you figure that all out?
As you said, a lot of spreadsheet math. But it took, I spent, I think, like the second half of I started early and trying to get things together, but I dedicated like most of the month of May to packing equipment and shipping things and getting people like hotels and planes and planning meals and things like that. So it is intense, and you kind of have to, we are close to Juneau, but we are like isolated. So
Folks at home want to know what you all.
Before we get to that, I just want to say that I don't think Zoe's giving herself enough credit because she planned. We did the math, and it was about 660 meals worth of food that we had to have all prepared before we came out here.
How many
That's
people?
a lot of meals.
How many people?
right now there's 15 people. Next block there will be, well, for a few days there will be 12, and then there's gonna be 8, and then the next block there will also be 8, and then after that more.
So it's like a varying number of people.
Yes, people come and go.
And this is like very intense SAT.
So to get to the what
And
do
they've
we,
also hosted our film crew, so we're working. I'm here, and we're working on a film coming out there next Thursday on Glacier. So, so thank you.
Yeah.
Made possible by viewers like it.
Yes.
And, so what do you eat?
Well, we've had some fresh meals for the last few days. So last night we had pesto pasta. The night before was taco night. It was Taco Tuesday.
Taku Tuesday.
Get it? Yeah. A lot of like minute rice. Pasta is easy to cook. We also
I
get
heard-
dehydrated.
I've heard a rumor that your favorite is dehydrated meals.
I wouldn't say it's my favorite. It's just more convenient, but I don't know. I think anything tastes good after you've walked 11 miles.
Yeah, but dehydrated meals are just meals you buy in a pack and add hot water.
Add some water.
it's a lot easier on the spreadsheet when you're just counting scoops
Yeah.
instead of ingredients.
Yeah,
At the end of a 14-mile day
right.
on the ice and the cold. Yeah, great. Anything else that you want to share with our audience before we go check out the drill rig?
I think you should go look at the drill. Yeah.
Yeah, all right. We're gonna go take a look at the drill before signing off here. So, we need our drill team though. Excuse the volume, I'm gonna have to call. Hey, Jake! Get over here!
Hey.
This is Jake Holmes. Jake, we're live. You're live on YouTube right now.
Hello, everyone.
You're from the University of Maine's Climate Research Institute. Yeah,
Climate Change Institute.
Climate
Yeah,
Change Institute. Thank you.
absolutely.
And you are the master of this contraption here.
Yeah, this is an old Army Corps of Engineers hot water drill that got decommissioned a few decades ago. And I do geophysics and electronic engineering tech at the university. So when they found it up in Alaska, they offered it to us. They pulled the old engineer, Bob Beagle, out of retirement. He and his wife, Sue, came up and spent a week with me rehabbing it. And
So let's
here we are.
take a look. So first of all, when you drill through ice, it's not like a typical drill that just sort of bores into the ice. How
No.
does it work?
Not at all.
Take a look
So
at it, though.
if you look right down here, this is a circuit, right? It's a system. So we start here. We have water on top of the glaciers, blue ice. So there's water everywhere. We pick that water up with a sump pump, and we bring it right.
So you
over
can see
there,
that-
white.
See that sump pump in there?
Bring it over to that white cube. That's our water reservoir.
White cube.
Yeah. So from there, it goes to the pump, which is a pressure washer and a cat pump. Then it goes to this boiler, which is an oil furnace, like you would find in the basement of your house if you live up north, right? It runs on diesel, and it has plumbing that goes through it. As the furnace fires, it heats the water to a little over 200 degrees, and then it comes out over here to our winch. Our winch has a couple 100 meters of Synflex hose, and this hose is really special because it's lined with Kevlar on the inside. It can take a lot of weight, right? So the hot water comes up, and we have a little depth counter up there. You can
Oh,
see a lot of zeros, maybe.
Probably can't hear you that far away. So the hot water goes up
The
through
hot
this.
water goes up the hose to that pulley, and you see a little depth counter on the left. It's at 0 right now because we're at the surface. There, it comes to the drill stem. All right. This drill stem is solid brass, except for a small hole down through the center. Brass is very, very heavy, surprisingly so. And that's good because what we want is a straight hole. If we have a heavy weight on the end of our hose, it'll help us keep that hole straight as we go down. The pressurized water comes out of the tip at about 8 to 800 pounds per square inch.
Let's take a look at that tip here.
Ah,
So,
yeah.
so water comes out of that thing right there, and it's that hot water that goes down this hole.
Yep.
You can see that hole.
Yeah.
Wow, that's quite a hole.
So if you're looking at it from this angle, it might look like it gets skinnier as it goes down. Well, that's not a trick of the camera. What that is ice will melt from convection of the water, movement of the water, right? And since this ice at the surface has had longer time in contact with moving water, the borehole is widened. Down at the bottom, it's probably only about this big. Up here at the top, a bit wider.
Okay, so you make this borehole. This is where we send the scientific instruments that you just heard about from Zoe and Jaiden down. Now, I have an important question. I've heard that you're able to turn this into a hot water shower.
That is
Explain.
okay. So one of the advantages to this system is that it's modular. You can reconfigure it for all sorts of different environments and purposes. Drilling a borehole and seeing what's happening at the bed, that's the primary mission. After that's done, we can hang up a tarp. We have a plastic pallet over here, and the team can celebrate with a hot shower. Pretty easy.
Sounds amazing.
Yeah. I mean, the important thing is trying to get to the bed. And one way or another, every one of us out here is here trying to figure out the movement of the glacier, right? The glacier moves from the force behind it and how it slips along the bed, all right? We need to be able to get down there and take a look, put instruments down. We can see what the water pressure is down there because the pressure of the water under the glacier tells us a lot about how it will move, right? We're trying to pull sediment up from the bottom, and that will tell us a lot about why it moves the way it does in different areas because there's different sediment qualities on one side of the glacier and different water pressure than there is on another side of the glacier.
And how do you get all this stuff up here?
Lots of helicopters. Yeah.
Very cool.
So these sleds weigh anywhere from 600 to 900 pounds a piece. We hook them up on helicopters and we sling load them underneath the helicopter. Yeah.
Well, let's take one last look at this hole. Are you going to start going soon?
We are going to start going soon. It gets kind of noisy when we do. So
All right. So we've got to stop this live stream so you can get back to work.
would you like to see any of these?
Oh yeah, show us how heavy these things are.
Yeah, I mean, so these are spare drill heads. So we have different stems for different lengths, and we have different tips for different purposes. This is called a reamer. We use it specifically to make the borehole wider for larger instruments. Okay. After this is the tip that's on there now, similar, very close. And this will make a skinnier hole because all the water is directed down. This will direct the water out. After we get done.
And these things are super heavy, yeah?
Yeah, very, very heavy.
You can get your workout done
Yeah.
with those.
Absolutely. The next piece of instrumentation we put down after we reach bed, we suspect we do. We need to verify before we put anything down. Some of this equipment is very expensive. This is an optical televiewer.
Ooh, so video.
this is one of the coolest things out here. Okay, this is a plow meter. This instrument right here will go down. It'll take a 360-degree picture of the borehole all the way down. Now, inside here is
Well, that will be in the film.
yeah.
But not on the live stream.
There's also an inclinometer in here. An inclinometer tells us whether we're straight up or down. That will verify for us how well we drilled our hole. After this goes down, it'll take a picture of the bed, and then we'll move on to sediment pouring devices and things like that. And after that, we'll start putting sensors down for these folks. They have these guys have some really, really cool tests that they're doing that are not as complicated as all this high-tech stuff that we have. They get really great information with low-tech instruments. It's kind of neat.
Super cool.
Yeah.
Well, thank you, Jake. Thanks for giving us a tour. I want to let you actually get to work.
Thank you so much.
And thank you to all you Nova fans who joined us live on the Taku Glacier today. We've got to sign off. This team of this nice crowd has to start planting seismometers. So thank you so much. And check out the film. It'll be coming out around Earth Day of next year. We don't know the title yet, but it'll be the one about glaciers. All right. Thanks, everybody.